Hello students, welcome to the online lecture series of St. Andrews Institute of Technology and Management, Gurugram. Myself Sadendra Vats, Assistant Professor in ETC Department. In today's video we will see some of the basic properties of the systems and the LTI system, which is a part of Unit 1st of Signals and Systems, EE 4th semester. So what is a system? So a system can be defined as an interconnection of components or some devices or some subsystems in which we feed the signal and the system transformed this signal into some another form. So input signals are transformed by the systems or cause the system to respond in some way, resulting in other signal as output. So as you can see in diagram, I am feeding signal xt to the system and it is providing yt. Yt can be anything which a system is performing the operation on xt. It may be a delayed function, it may be advanced function, it may be differential function, it may be integration. So system can perform any type of operation on the applied input. So if it is a continuous time signal, it is denoted as x of t, and if it is a discrete time signal, it will be denoted as x of n. Similarly, for continuous time system, output will be denoted as y of t, and for discrete time system, output would be denoted as y of n. So let's say if I am providing xt as input to the system and it is giving me output yt, which is x of t minus 1. So if I calculate y of 1, that is the value of output at t is equal to 1, then it comes out to be x of 0. Okay, that is the output is depending upon the past value. When I was calculating at t is equal to 1, it is giving me the input value of t is equal to 0. So the system is depending on the past value. Similarly, for yt is equal to xt, it is depending on present value, and if the system provides me xt plus 1, then the output is depending upon the future value. So first is static and dynamic systems. In static systems, if output of system depends only on present values of inputs at each and every instant of time, then the system will be called static. That is, if the output at any instant of time is depending upon the present value only, then it is called the static system. So these systems are also called memoryless systems, as the output is depending only upon the present value and not on the past or future values. Okay, similarly, dynamic systems, if the output of system depends on the past or future values other than the present values, then it will be a dynamic system. So if at any instant of time, if our output is depending upon the past or future value, then the system would be dynamic. Now let's see some. So these systems are also called system with memories. Let's see some examples. If our output is depending on xt plus xt minus 1, so system would be dynamic as it is depending upon the past values. Similarly, if it is yt is equal to x of sin t, then it is again dynamic. Okay, yt is equal to e1 of xt, so it would be dynamic again, as e1 part of xt we already know we can calculate as xt plus x of minus t divided by 2. So this value would be the past value, so this is dynamic again. If I say yt is equal to real of xt, then the system will be static. Okay, so integral and derivative systems are always dynamic in nature. In case of time scaling or time shifting, the system will be dynamic. That is, if I say x of 80, or if there is a shifting operation is there in the system, then the system would be dynamic. Now comes causal and non-causal systems. So causal system, if output of system is independent of the future values of input at each and every instant, then the system will be causal. That is, the system is the causal system. In causal systems, output only depends on the present value or the past value. It will never depend on the future values. So these systems are practical and realizable systems. Okay, example, if I say yt is equal to xt, which is depending on present value, yt is equal to xt minus 1, which is depending on past values, and yt is equal to xt plus xt minus 1, which is depending on present and past values. So none of this system is depending upon the future values. So all these systems are causal. Whereas if the output of system depends on future value of input, then it will be a case of non-causal systems. Like if yt is equal to xt plus 1, or yt is equal to xt plus xt minus 1, xt plus 1. So at any instant of time, if our system depends upon the future value, then it will be non-causal. Then comes anti-causal. If output of system depends only on future values, that is, if output depends only on future values, then the system will be anti-causal, as yt is equal to xt plus 2. So all anti-causal systems are non-causal, but converse is not true. That is, all non-causal systems are not anti-causals. Okay. Now the next one is linear and non-linear systems. So linear system, a linear system follows the law of superposition. So this law is a necessary and a sufficient condition to prove the linearity of systems. So it consists of two laws, that is law of additivity and law of homogeneity. So first is law of additivity to prove whether a given system is linear or non-linear system. So if I have a system in which if I provide x1t, it gives me y1t, and if I give x2t, it gives me y2t. Okay, so at the output I add both of these to get y1t plus y2t. Now if I provide the same system, the summation of these two systems, that is x1t plus x2t, I have added both and then feed it to the system, that is x1 plus x2. So I am now feeding x1 plus x2t, and if the system provides the same output, that is y1t plus y2t in this case also, so both of these outputs are equal, that is y1t plus y2t in the first case and y1t plus y2t in the second case, then the system will be linear. Okay, example, let's see an example. If yt is equal to xt plus 10, yt, our system is providing output which is adding 10 in the input, that is xt plus 10. So output is input plus 10. So if I provide x1t, then y1t would be x1t plus 10. If I provide x2t, output would be y2t plus 10. And now if I add them, I would get x1t plus x2t plus 20. On the other hand, if I provide the linear combination of these signal to the system, that is x1t plus x2t. So if I provide x1t plus x2t, the system will add 10 to the input, so it will provide x1t plus x2t plus 10. So as we can see, these outputs are not equal. In this first case I am getting 20, in second I am getting 10. So this is a non-linear system. So this is how you can check the linearity using the law of additivity. Then comes law of homogeneity. Okay, if I provide xt input to the system which provides output yt, and if I now multiply it with a constant k, so it would be kyt. So in second case, if I multiply the input in advance, that is kxt, then feed it to the system, then if output comes kyt, then the system is following the law of homogeneity, that is kyt is equal to kyt. If this is not the case, then the system will be non-linear. Let's see how. If our system is providing output as square of input, so output is square of input. So if I provide input to the system directly, it will provide x square t, and now I multiply it with using k, so it will be k x square t. Now if I provide k into xt to the system, that is I have multiplied k in advance, k xt to the system, so it will provide the square of input, that is it would be k square x square t, which is not equal to the output of first case, so it is non-linear. Okay, so we can see one example on that. If yt is equal to x of sin t, then in this case, if I have taken both the cases, that is the linearity and the homogeneity as well. So if I provide x1t, I will get x1 sin t. If I provide x2t, I would get x2 of sin t, that is t is replaced by sin t in the output. So when I add, I get x1 sin t plus x2 sin t. Similarly, if I provide the linear combination, that is x1t plus x2t, so I would get, as t is replaced by sin t, so both the outputs are same. So system is linear. We can also check the homogeneity law as well. If I provide xt, it would give me x of sin t, then I will multiply k, so it would be k x of sin t. Similarly, initially if I multiply k into xt, it would be kxt. Now I feed it to the system, so t will be replaced by sin t, so it would be k x of sin t. So both are same because we are replacing t with sin t. So you need to be careful while doing all these things. Okay, so this system will be linear. So linearity of system is independent of time scaling, that is if we are performing time scaling, then the system would remain linear. Linearity of the system is independent of coefficient used in system relationship, so it is independent of the coefficient used. Some more properties are there. Integral and derivative operators are always linear. Even and odd operators are also linear. Real and imaginary operators are non-linear. So you need to remind all these things. For linearity, output should be 0 for 0 input. So this is one more condition. So output should be 0 if you are providing 0 input. There should not be any non-linear operation. Okay. Then comes time variant and time invariant systems. So in time invariant system, any delay provided in the input must be reflected in the output of the system. So as we can see, if I provide xt to the system, it gives me output yt, and if now I provide delay t naught in output, so it would be yt minus t naught. In second case, if I provide delay to the input itself and then feed it to the system, so whatever the output comes, if it is equal to the first case output, then the system is time invariant, as the delayed in input is reflecting in output as well. So this is the condition for the system to be time invariant, otherwise the system would be time variant. So any delay provided in the input must be reflected in the output of the system. So let's take an example. If yt is equal to x of 2t, that is if I am providing xt, system is giving me x of twice of t, that is it is performing scaling function. So if I provide xt, I would get x2t, and then I provide delay, it would be x2t minus t naught. In second case, if I provide delay to the system, input, then it will be xt minus t naught, and then if I feed it to the system, it will scale it. So 2 will be multiplied in the variable t only and not in t naught. This is need to be taken care of. Okay, 2 will be multiplied to t only. So we can see that both these outputs are not equal, because in one case I am getting x of 2 t minus t naught, and on the other case I am getting x of 2t minus t naught. So both are not equal. In this case I am getting 2t minus t naught, and in this case 2t minus t naught. Okay, so both cases are not equal, so system is time variant. Another example, if yt is equal to x of cosine t, so you can see we are getting in first case x of cos t minus t naught, and in second case x of cos t minus t naught. So these outputs are not equal. So what our system is doing, it is making t cosine t, xt is becoming x of cos t. So it is a time variant system. So in case of scaling, system will be variant, time variant. If coefficient of system relationship is a function of time, so if coefficient is a function of time, that is in this example yt is equal to cos t xt. So the cosine function, which is a coefficient, is a function of t, so it will be time variant. So whenever the coefficient of our input is time dependent or the variable dependent, it would be time variant. Now comes stable and unstable systems. So a system must follow the bounded input bounded output criteria, that is for bounded input output must be bounded. So then our system would be stable. Output should be finite or bounded for finite input or bounded input at any instant of time. So example are unit signal, any DC value, sinusoidal functions or signum function. Integration and differentiation signals or unstable systems. Okay, now let's see the linear time invariant systems. So LTI systems are those systems which are following the both these conditions, that is it is linear as well as time invariant. It must be linear as well as time invariant. So our system would be LTI system. So there are some terms which we would use in the LTI systems. One is the impulse response of system, which is denoted by h of t in time domain, and h omega or h of s, that is transfer function, which is denoted in frequency domain. So if I providing xt, it is giving me yt. This is a LTI systems. So impulse response and transfer functions are used for LTI systems. So what is impulse response? Impulse response is nothing but if I provide our input in the form of a impulse, then whatever the output would be, that is h of t, this would be my impulse response to the impulse input. Okay, so impulse response is used for defining LTI systems in time domain, and transfer function is used for define LTI system in frequency domain. So what is impulse response? If I am providing delta t as input, I am getting ht, which is the response. So impulse response can be defined as the output of a system when unit impulse is applied to the input of system. Okay, transfer function, it is the ratio of the Laplace transform of output, that is y of s, upon the Laplace transform of input, that is x of s. So it would be h of s. H of s is equal to ys upon xs. Okay, when all the initial conditions are 0. So hs is nothing but ys upon xs, which are the Laplace transform of output and input at 0 initial conditions. So total output is equal to 0 input response and 0 state response, where 0 input response is due to initial condition, which is 0 in this case, and this is due to the applied input. For linearity of systems, initial conditions are assumed to be 0, because if initial conditions are non-zero, then our system may be non-linear. Okay, so one of the main properties of a LTI system is convolution. If I am providing input xt, it is giving me yt, whereas ht is the impulse response. Xt can be any other input now. Okay, so yt would be xt convolution ht, where xt is the input, which can be any input signal, and ht is the response to the impulse input, as we have seen earlier. Okay, so yt would be xt convolution ht. So convolution is nothing but the overlapping of two signals. Okay, so convolution is a linear time invariant operator, and it is used only for LTI system. So yt is given as xt, this is the convolution sign, ht. So it can be given as integral minus infinity to t h tau x of t minus tau d tau. I have changed the variable the integral t to tau, that is d tau. So I am integrating it in respect to tau. So it would become h tau into xt minus tau d tau. So this is the condition for yt. So condition for LTI system to be static. So our system would be static if yt, that is the output, is k into xt, or if it is input is del tau, then ht will be k del tau, that is the transfer function is of the form of a constant k. That is, if I am getting impulse response at t is equal to 0, that is I am getting the impulse at t is equal to 0, then it will be static. Okay, or if I am getting a transfer function of this form, so it will be static, otherwise it will not be static. So as we can see in example, for static LTI systems, impulse response should be at origin, and transfer function should be independent of frequency. Okay, so transfer function, that is h of s, should be independent of frequency, and the impulse should be at origin. So this is the example. In this case you can see impulse is at t is equal to 0, that is 2 is the value, and in this case it is dynamic or non-static, as that impulse is coming at t is equal to 2 second. Okay, similarly this signal is dynamic, and this signal hs is equal to 2, as it is not depending upon frequency, is static, and this system hs is equal to 1 upon s plus 1 is dynamic, as transfer function is depending upon the frequency. Next is condition for LTI system to be causal. Okay, so if, as we know that yt is equal to xt convolution ht, which can be written as h tau xt minus tau d tau. So for the LTI system to be causal, this is the condition, that is our impulse response should be 0 for t less than 0. So for t less than 0, our impulse response should be 0. We should not get anything beyond here, that is in the left part of the plane. So ht should be 0, that is it should be 0 for t less than 0. Okay, for the system to be stable, it should be ht should always be in the right part. So if we can say this is for the causal condition, for causal, that is if ht is comes like this, that is in the right plane, so it will be causal. If transfer function or we say impulse response is comes like this, ut plus 1 minus ut minus 1, it is coming in both sides, so it is non causal. It must always be in the right hand side for the system to be causal. Okay, that is it should be ht should be 0 beyond t less than 0. Okay, so last one is condition for stability of the LTI system. So if our impulse response of LTI system is absolutely integrable, if the impulse response ht is absolutely integrable over the whole range, then the system would be stable. So we can check it using the ht and integrating it with respect to time. So if it comes completely integrated, then our system would be stable. So this is it for the lecture. I hope you understand. Thank you very much.